Okay, so we're going to continue where we left off in section 3.2, talking about linear functions. Okay, can somebody remind me again what linear means?
Line.
Line. All right, so on the test, if they ask you to describe whether or not something is linear, you're looking to check if it's a
Line.
If it's a line. Yep.
Mr. Hager.
All right, so first thing we're going to look at is what's called a solution of a linear equation. Okay, so you should have a spot on your reference sheet to write that. Okay, a solution to a linear equation.
Well, that sounds cool.
Yep, it's an ordered pair. Okay, it's a coordinate that makes the equation true.
Okay.
Okay?
So guys, on your note sheet, you see it has A, then it's blank. You're going to write what's involved. Solution of a linear equation in two variables.
Right. So, in other words, you have to have a value you plug in for x and for y that makes this true. Okay? Does anybody see, and there's thousands of examples that would work, but does anybody see a value I could plug in for x and a value I could plug in for y
W and X?
that would make it
Oh, wait.
True.
We already have X.
You want to see a number you could pick for x and a number you could pick for y. You plug them both in, and it comes out to 8.
Oh. 2 and 1.
Right? So x could be 2. Yeah, I agree with that.
Y would be 1.
No, guys, we're just showing you how, you don't have to worry about writing the example. We're just showing you guys how it works right now.
Okay, the only thing is if you pick 2 for x, you're going to have to pick a fraction for y. So now we've kind of backed ourselves into a corner with a fraction.
1 for X.
Oh, 1 for x. Okay, that's
Great choice.
going to work. And what could you pick for y? 2. This is one ordered pair that would make this true. What's 2 times 1?
2.
And what's 3 times 2?
6.
And then 2 plus 6. Here's my 8. Okay. Here's another one you could pick. Let x be 4 and let y be 0. What's 2 times 4? 8. What's 3 times 0?
0.
And then 8 plus 0. Here's my 8. Okay. Here's another one. Okay. There's a ton of these. There's thousands of them. Okay. That's an example of an ordered pair that makes that equation true. Okay. So any questions on that?
Nope.
So if I want to make a graph, okay, of something that looks like this, okay, basically what we're graphing is every single point that makes this true. Every one, not just these two, all of them. Okay, thousands of points. So when you start to put thousands of points together very close, what do you get?
A line.
Yeah, you get a line. Right? So if you could take every single point that makes this true, including these two, and put them all together really, really close, you would have a picture of a line. All right. And in fact, that's probably an easier way to find solutions. Draw a picture of this. And then once we have a picture, we can look at the graph and we can find the solutions. All right, so the next thing we're going to talk about is what kind of values you're allowed to plug in for x. And we're going to talk about 2 different words. Okay. The first one we're going to talk about is what's called discrete. Okay, so it says sometimes the domain of a function is discrete. Okay, what that means is you're only using certain numbers, specific numbers.
Guys, you have two blanks on your sheet for that second bullet. So you're going to write for the first blank, you're going to write discrete. Then after or, you're going to write only contains certain numbers. And then also you're gonna remember at the last blank there, where it says let's graph all integers from, you're gonna write in 1 to 5.
Okay, so first what I'll do is I'll show you a picture of something that's discrete. Okay, we'll look at a picture. So this one is saying to graph all numbers from, all integers from what to what? 1 to 5. So what's the first one? 1. What's the next integer after 1? 2. How come I don't do 1.5?
Because it's not on the graph.
Well, it's on the graph in between 1 and 2. But it's not an integer. Okay, they said to graph integers. Integers are not decimals. So you're going to skip every decimal between 1 and the next integer is 2. Okay, what's the next integer after 2? 3. Why not 2.7? The 2.7 is not an integer.
Because you said so.
Right? And then the next one after 3?
4.
4 and 5. This is a picture of what a domain that's discrete looks like. Discrete means it's certain numbers. Okay? And there's a lot of gaps between the numbers. Right? Here's another example of something that's discrete. Let's say I start counting, okay, the people in this room. Okay, so I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm counting people. Did I? Well, there's more. But did I list every single possible number between 1 and 10? No. I didn't say like 6.7. I didn't say 9.3.
Too much work.
Right? I didn't say all those. Okay? So what I did is I counted, but there were lots of gaps. Okay? That's discrete. Can anybody think of something else in real life that would be discrete? Where you don't use, you skip a lot of numbers as you do it.
A ruler.
A ruler, yeah, a ruler is definitely discrete. Okay, so if we take, let me see if I have a picture of a ruler. All right, let's see.
That's cool. And that sound just
Ruler.
satisfying.
All right, let's look at a ruler. Okay, so if you look at a ruler,
It's
okay, there's certain measurements on it, okay, like 1, 2, and there are some in between. But is there every single number between 1 and 2 represented here?
No, because they're lazy.
Because they're lazy?
Yep.
So on a ruler, rulers are only so accurate. This ruler, I think, measures to the nearest 16th of an inch. There's nothing in between. Like, if I zoom in, let's make it really big.
Whoa.
There's nothing in between here and here. There's a gap. So anything that has gaps in it, that's discrete. Okay? Even if you had a ruler that had more marks on it, there's still gaps. It might be a smaller gap, but it doesn't cover every single possible number. So if I were to measure, say, the length of this line, okay, as I try to measure it, it's in between 2 marks. So I'd have to round it off because this ruler is discrete. Okay? It's not as accurate as I need. Anybody think of something else that's discrete? Something you all do every Friday usually.
Sleep.
Well, you sleep every day, I hope.
Yeah.
Maybe.
What do you do in school on Fridays usually?
What do you mean?
Try not to sleep.
Take a test. Okay? And when you take a test and you get your grade, there's only certain grades you can get, right? When you get a test grade, at least for me, you get a test grade that's an integer. You might get an 82 or an 83. But do I ever give you a test back and give you like an 82.1?
I've had teachers that do that.
Do I do that?
No.
Does Mr. Roy do that?
Yeah.
No. He does?
They round up around.
Yeah, they round it, right? They take your grade and they round it off, right? So there's gaps. You're going to get an 82 or an 83. You're not going to get anything in between. So test grades are discrete, right? Because there's gaps. Right? So that's the easiest way to think of discrete. Discrete, think gaps. A lot of times no fractions, no decimals, just integers. All right, so let's take a look at something a little different.
No, don't shrink it. It's cute.
Okay. Another kind of domain we can have besides discrete is continuous. Now, continuous means no gaps. It means every single possible number between two numbers is included. Okay, and I'm going to do the same thing. I'm going to show you a picture of a continuous domain. This time, let's not graph all integers from 1 to 5. Let's graph all numbers. Not just the integers. Let's graph every single number from 1 to 5.
Okay, you want to start with that?
Well, as long you've got this graph, so I'm going to graph all numbers from 1 to 5. As long as you know what I'm graphing, that's fine.
Just pop it down words, though.
You just have to fill in continuous, right?
No, there's another blank.
Oh, there's another blank? Okay.
Contain the numbers in certain intervals.
Can I please have everyone's attention? We're extending.
Okay, so I'm going to start at 1. Okay. Is 1 a number between 1 and 5?
Number between.
No.
Well, is it either between or is it one of the numbers on the ends? Yeah. How about 5?
Yes.
Yeah. What's another number between 1 and 5?
3,
Sure. Another number?
2, 4,
4? Give me more.
none.
A lot more.
0.5.
2.3.
0.5. 2.3. Give me another one.
0.7.
0.7. Okay. What else?
5 and 5/16.
We got to stay between 5, Mr. Roy. Up to 5.
Line over the crossing.
4.5.
4 and 5/16.
Can we just put a big line over the
4
crossing?
and 5/16. Yeah. Kyle, what did you just say to do?
Put a line over the crossing.
Just put a big line over everything.
Why did we do that? Really? Then why'd you make us do the dots? There you go, Kyle.
I don't know.
Because my thinking is.
Why did we have to draw a line for the other one?
Why did you have to draw a line? Because that one was only certain points. It wasn't all of them. But this one says all. Okay, so when you say graph all numbers, that includes any number you can think of between 1 and 5. Here's an example of something that's continuous. Okay, you've got, say you got a pot of water, okay, and you're gonna bring it to boiling. You're gonna cook some pasta. Okay, let's say when you put the water in the pot, I don't know, it starts out at, let's say maybe room temperature water, like 70 degrees. Okay, so you put the water in the pot at 70 degrees. Okay. As it boils, the hottest it's going to get all the way up to boiling is 212. As the water starts to boil, what temperatures is it going to go through? As it starts at 70 and ends up at 212?
A lot.
How many?
Over 100.
Can I please have everyone's attention?
So think about that for a second. As the water starts at 70 degrees and it starts to warm up, what temperatures will it go through? How many?
There's 142 different temperatures.
142 different temperatures. I think there's even more. As you go from 70 degrees all the way to boiling, how many temperatures?
All of the things. I'm so bad.
Yeah. What'd you just say, Kyle? Yeah, there's infinite temperatures. Okay. As you're going to hit 86 degrees at some point. You're going to hit 130 degrees. You're also going to hit 154.7 at some point. Okay. You're going to hit every single possible number you can think of between 70 and boiling. There's no way to skip anything. You have to go through every temperature.
So I was right.
Does that make sense?
Is that right?
When water's boiling? You can't skip numbers, and you can't all of a sudden have water at 70 and then have it boiling and it's going to jump to 75.
Was I right though?
What'd you say?
I don't know.
Oh,
I forgot.
I don't know. Okay.
I'm too tired to remember.
So boiling is a continuous process. You don't skip anything in between.
Yeah, but so continuous, guys, if you're doing problems that deal with like units of measure, like, you know, it might be centimeters, it might be, could be a temperature, it could be, you know, 100.2 degrees, right? So anything that can be measured like that, that's going to be continuous. Anything that's discrete, we're talking about shirts, number of candy bars sold. Those are actual whole things. You can't cut them in half. They can't be measured as a fraction or a decimal. So those are going to be discrete.
Anybody think of something else that's continuous? Like a situation where it's continuous.
Life. I just know.
Okay, your age. Your age is continuous.
Life.
Yeah, so your age, right? Because as you, let's say you,
Right.
you're 10 years old one year and you're 11 years old next year. You went through every possible age between 10 and 11. You were 10 and a half at one point,
Science.
10.4, 10, 10 in 1 day, 10 in 1 day and 10 seconds, 10 in 1 day and 10 seconds and 3 milliseconds. It's continuous.
When they're like describing how old their child is, and I'm like, oh, yeah.
All right, so, okay, guys,
2 days.
what does discrete mean? When you're measuring something that's discrete,
Space in between.
there's gaps. If I count the number of cabinets in this room, there's 1, 2, 3, 4, 5, 6, 7, 8. I don't have 7.5 cabinets. I don't have 6.1 cabinets. I have gaps, okay? Whole numbers, okay? All right, so we're going to look at how we make a graph, okay? Depending.
Those steps, you got to write them on your note sheet.
We're going to look at how we make a graph, and we're going to set up a table to do it. Okay, our table, just like you had in the homework a couple nights ago, it's got 4 columns. It's got a column for x. It's got a column to do the formula, show the work. It's got a column for the y. And then it's got a column for your coordinate.
And guys, write in on your little, you have that little table on there. Make sure you write in what each thing is.
When you try to play out and mess up on your spelling, but it ends up looking bad.
At this time, students can proceed to
All those people just go back.
All right, so when you're going to make a graph, step 1, draw your tape, make your table. Step 2, we're going to fill in all the rows in this table. Okay, so we're going to have something. Well, you know what? I'll show you the next example. We're going to make the table. Once you have the table, you are going to graph all the coordinates in that column. And step 3, a lot of times they're going to ask you in the problem, is your domain discrete or is your domain continuous? Meaning, are there gaps in the domain or can you plug in any single number you want? Fractions, decimals, things like that. All right, so let's take a look
Please don't change it. Oh, no.
at this.
Wait,
Okay.
oh.
So first example, it says the function y equals 15.95x represents the cost in dollars to buy X tickets to go into a museum. Each customer is limited to buying a maximum of 4 tickets. So step 1, we're going to find the domain of the function. Okay, does everybody have what's on the left?
Not yet.
No.
I am on
Okay, so when the problem asks me about domain, which letter are they talking about? They're talking about X. Okay, so in this problem, what does X represent?
X equals the domain.
X is the domain. And what specifically is it in our word problem? Josh? It's the number of tickets. Okay. Is there a maximum number of tickets that a person is allowed to buy?
4.
4. So when I write my domain, 4 is the maximum number of tickets they can buy. What's the least number of tickets somebody could buy?
1. 0.
Yeah, 0.
What?
They could decide they're not going to go to the museum.
Yeah.
Right? What else could they buy? They could buy 0 tickets. 1, 2, 3, or 4. Now, could they buy numbers in between? Could they buy 2.6 tickets?
No.
No.
Unless you want to have.
Right? So we have gaps here. Okay? So if you have gaps, is that discrete or is this continuous?
Discrete.
This is a discrete domain. Okay, and now I'm going to make that table. I'm just going to try to squeeze it in. I'll just put it right there.
Why don't you put it below it?
What's that? Below? I have a graph down below. All right, so my input. What are the 5 values that I'm allowed to use for x?
0, 1, 2, 3, 4.
0, 1, 2, 3, and 4.
That's why you didn't put it there.
All right? Now you're going to take each one, and we're going to plug them into our formula. So the formula is,
I'm confused.
what's up, Jordy?
Do we write that down?
This table?
Yeah.
I would make the table because we're going to do a
Yeah, you
graph.
don't have the table on it, you have to make it.
Oh.
Okay, what are we plugging in for our first value of x? 0. What are we plugging in for our second value of x?
Wow, I actually hit it. That's surprising.
Go ahead, tell me, Aiden, what are you plugging in for your second value for x?
1,
Yep. How about your third value?
2,
Yep, next one.
3,
3, and the last one?
4.
Times 3, and y equals 15.95 times 4. Okay, so that's showing the work we're going to do. What's 15.95 times 0? Careful.
Oh, 0.
Anything times 0 is 0. 15.95 times 1. 15.95. Now 15.95 times 2, let's use the calculator. $31.90. Okay, if you times it by 3, $47.85. And times it by 4, $63.80. Okay, so now we have a column of x's, and we have a column of y's. Okay, the column of x's is how many tickets you buy. The column of y's is the cost to buy that many tickets. So now we can organize it as ordered pairs. What's the cost to buy 0 tickets? $0. What's the cost to buy 1 ticket? 15.95. Okay. Cost for 2 tickets.
31.90.
$31.90. 3 tickets.
47.85.
$47.85. And
63.
4 tickets is $63.80.
That is not as pricey as most tickets could be.
Yeah, it just depends on your museum, but. Okay, so these are the 5 coordinates that I'm going to try to graph. What's my biggest x value? Okay, that's not bad. What's my biggest y value?
63.80.
Ooh, 63. Okay, that's pretty high. So what I'm going to have to do on my graph is, I can't go by ones because my graph only goes up to 10. Yeah, I could go by tens. 10, 20, 30, 40, 50, 60, and 70. That's high enough. And I'll go by ones here. So this is tickets that you buy. And then this is cost. Okay, somebody tell me quickly, how much is 0 tickets? $0. 1 ticket. Yeah, about $15.95, so we'll just estimate it. 2 tickets.
31.90.
All right, so a little above 30. How about 3 tickets? 3 tickets is $47.85, just going to estimate it. And how about 4 tickets?
63.80.
$63.80. Okay, does it look like those points are in a line?
Yeah.
Hey, it's not perfect, but it's pretty close to a line. And that's it. Now, should I connect them? Okay, if I connect them, that means that I can buy in between 1 and 2 tickets.
No.
No, I can't buy 1.6 tickets. Anytime you graph something with a discrete domain, it should just be dots. Don't connect it. Okay, so think in your head, discrete equals dots. Discrete,
Now I
dots.
want to connect it.
Now what?
Now I want to connect the dots.
Well, we're going to do one where you connect the dots too.
You tell me not to do it, not.
Okay, any questions on that one?
Nope.
Okay. Does everybody have the table? Next one. Okay, this one we are not going to graph. Okay, we're going to do everything but the graph if I had the graph on here. Yeah, we'll skip the graph. Okay, it says this function represents the amount in dollars of money you have after you buy a certain number of DVDs. So you're starting with $50, and every DVD that you buy is going to cost you $9. Now, if you only have $50, can you buy as many DVDs as you want? No. So there is a limit. Like you can't buy 200 DVDs. You don't have enough money for that. So as we go through it, we'll figure out how many can we buy with $50. All right. So let's look at our domain. What's the domain in this problem? What letter? It's D. Normally we use X, but in this case it is D. And D represents what?
DVDs.
How many DVDs you buy. So think about when you buy DVDs. Would that be discrete or continuous? So continuous means you could buy any number in between, like 1.7, things like that. This is discrete, right? Because you could buy 1 DVD, you could buy 2 DVDs. You can't buy anything in between 1 and 2. You can't buy 1.7, not with DVDs, okay? Kind of like buying, gallons of paint at the store. You can buy 1 gallon, you can buy 2 gallons. Unless they sell smaller containers, you can't buy anything in between 1 and 2 gallons, right? You gotta buy 2. All right. So let's see if we can figure out our domain. How many DVDs could you buy at a minimum? The least number you could buy.
Everyone.
Well, I could walk into a store and say, I'm not buying any.
Oh, 0.
0. Right? So that's the smallest amount of DVDs I could buy. Do I have enough money to afford one DVD? All right, so you know what? Why don't, to save time, as we list our domain, let's put it in the table at the same time. So 0.
Really, I just wrote.
So now the cost, you know what? We won't, I'll even shorten it up. This is the cost. 50 minus 0. What is 50 minus 0? 50. And lastly, what would my coordinate be if I buy 0 DVDs? It would cost me how much? Cost me 0. So how much money would I have left? I'd have $50 left. If I don't buy any DVDs, I'm going to have $50 left. Okay. Do I have enough money to buy one DVD? Yes, I do. If I buy one DVD, it's going to cost me $9. How much money would I have left after buying one DVD? Well, I'm only starting with 50, so I can't make money. But yeah, I'd have 41. All right. So if I buy one DVD, I'm going to be left with $41. Okay. Do I have enough money to buy 2? Yeah, I can buy 2. How much money do I have, or how much does it cost me to buy 2 DVDs? Each DVD is $9. So what's 9 times 2? 18. So if I spend $18 on DVDs, I have $32 left. Mr. Rowe, you want to do a continuous one? It's up to you. Let me know.
So now.
How about 3 DVDs? Could we buy 3? Yeah. What do we have to make sure when we're buying DVDs? We just have to make sure that we don't what?
Overspend.
Yeah, we don't spend more money than we have. Okay. So just to kind of help you guys out, I'm going to tell you you could buy 3, you could buy 4, you could buy 5, and that's it. Okay. You won't be able to buy a 6 DVD. You don't have enough money. So 50 minus 9 times 3. 50 minus 9 times 4. 50 minus 9 times 5. We just have to do each one of those. Can somebody help me? What's 9 times 3?
27.
So let's do 50 minus 27. That leaves me with $23. What's 9 times 4?
36.
So 50 minus 36 leaves me with $14. What's 9 times 5?
45.
So, and 50 minus 45 only leaves me with $5. That's why I can't buy a 6 DVD. Okay, I'd go negative.
You can buy those $5 DVDs.
You could. Maybe you go get a $5 DVD at Walmart.
They're junky.
No, I don't.
And that, right there, those are the points you would graph. Okay, again, I'm not going to do the graph this time. So did we say this was discrete or continuous?
Discrete.
Discrete, why?
Because it doesn't give you any in the middle.
Yeah, you can't get any in the middle, right? 2 discs or 3 discs. You can't buy 2.4 discs. Okay. And does everybody see why you have to stop spending money once you buy 5 discs?
Yeah.
You don't have enough money to buy another one, so you have to stop at 5.
You could go to another shop and get
right, let's take a look at this one. And this one we'll graph because it's a different graph.
We don't have a drive.
You don't have the graph on this one?
Nope. You chose the one that had the graph, not the graph.
We
Yeah, on
have
the
a
bottom,
graph.
bottom of the
It's
page,
way
guys.
down here.
Oh. I'm
What?
blind.
All right, this one says a cereal bar contains 130 calories. Okay, and the number of calories consumed is a function of how many bars you eat. Okay. All right, so first thing I want to know is if this is linear. So remember linear, what did we say about the slope? If something's linear, is it a constant slope or does the slope change all the time? Constant. The rate has to stay the same. So, the number of calories you get per candy bar is how much? 130. Does that ever change? No. As long as you keep eating the same candy bars, that is always going to stay the same. Right? So if you eat one candy bar, how many calories do you get?
You get fat.
130. What if you ate 2 candy bars? How many calories would that be? 260. What if you ate 3 candy bars? 390. Now remember what Mr. Roy and I showed you yesterday. If you're going to look if it's linear, check the x's. Are the x's going up by the same amount?
Yep.
How about the y's? How much are you adding each time? You're adding 130. So because the x's go up by the same amount and the y's go up by adding each time, this is linear. Yes. Okay, so if you're not sure, just make a few examples using your data. 1 candy bar, 2 candy bars, 3 candy bars. Now, I want to know if the domain is discrete or continuous. You're eating candy bars. So discrete means there's gaps. Could you eat between 1 bar and 2 bars? Yes. Could you eat 1 1/4 bars if you wanted? 1.1 bars? Yes. You can eat any number between 1 and 2 bars. So this is continuous.
Why did you drop one?
Yes.
Now I don't want to drop.
Okay. So this is continuous because you can eat any amount of bars you want. You don't just have to eat 1 bar or 2 bars. You can eat 1.5 bars. Okay. Well, the whole box. You can eat the whole box.
Eat the box.
I've never had one.
All right. So now let's graph the function using its domain. Okay. This time I'm not going to do the whole table because you guys already seem to get some of the points. 1 candy bar was how many calories? 2 candy bars. And let's just do 1 more, 3 candy bars. All right. Let's graph those points. Now, on my graph, I can go by ones here. That's okay. But what should I go by on the y's? Yeah, let's go by 50s. So 50, 100, 150, 200, 250, 300, 350, 400. Perfect.
These need to be bigger.
Can't fit it?
Nope.
It's a small grid. Well, you could just write off to the side the y-axis goes by 50s if you can't squeeze each number in. And then copy exactly what I'm doing. So 1 bar, 130.
Perfect.
Okay, 2 bars, let's see, 260. 3 bars is 390. Now the decision if we should connect them or not. Yes, because you can eat And actually, I didn't even put this one, but I could. What if you eat 0 bars? How many calories is 0 bars? 0 calories. Okay. So now,
Can you draw a colorful line?
you want it in color?
Yeah.
All right, I can put it in color.
I like teal. It's pretty.
All right.
Should I get blue?
It's
So,
one of my favorites.
so that line represents being continuous because you shade it in. You could eat 2.6 bars if you want. Okay, and see how many calories that would be. Okay, so that's continuous.
Oh,
What
last
time
two?
does this class end?
15 minutes.
So should we run it to
Okay, so any questions on that one?
Nope.
All right.
Is there a rainbow line?
So we're going to skip example 4. Okay, and your homework tonight, we're going to give you guys a little time if you need. Does anybody need to print it because they don't have a printer at home? Okay, a lot of people. So we'll give you at least 10 minutes so you can print it.
Guys, we're gonna give you, so listen to me. We're gonna do some review as well. So while we're working through the review, Jordy, what am I saying right now?
oh, we're gonna do the review.
Thanks, buddy. While we're working through the review, you can have your Chromebook out, and if you finish a problem or something, you can work on getting your printed. Right? Remember, it's what is it? Classroom.google.com, something like that.
Okay, guys, so don't forget to print your reference sheet on Google Classroom. We have the first test of the second quarter tomorrow, and both Mr. Roy and myself will be after school today.